So now let's discuss the convergence speed. So the theorem 4.1 tells us the convergence speed when we use low strongly convex mirror map. And this strongly convex means the strongly convex with respect to some general norm. So this does not necessarily to the Euclidean norm. So this can be any L norm and this can be any other norm. And FB convex and Rips is continuous again with respect to some general norm this. And when we let R square is equal to supremum of pi x, the pi x function value and pi x1 function value, so which is basically kind of diameter of your mirror map function, then mirror descent algorithm with this step size can guarantee this. Again, we cannot use Ras times law because for this theorem we cannot guarantee fxt plus 1 is less than or equal to fxt. This is not for this case. So this was a well-known convergence result for mirror descent algorithm for ellipsis continuous case. This is also very interesting result, and I will leave the proof for your practice. This is kind of homework, so I will give you the exact proof next week. I would like to introduce another very interesting result for mirror descent algorithm, which is shown very recently by Ohad Shamir et al. In the paper Communication Efficient Distributed Optimization using an approximate Newton time method. So in theorem 4.3, what is the result is when the Bregman divergence of original function f between any point x and x prime is lower bounded by alpha and upper bounded by beta times the Bregman divergence with respect to the mirror map function pi, then with this step size, 1 over beta step size, we basically can guarantee exponentially decreasing error value. So this result almost the same with the case alpha strongly convex and beta smooth. Indeed, this condition means we have this. The Hessian of function f is upper bounded by beta times Hessian of pi function and alpha times Hessian of pi function. So here this notation means so when A matrix is less than or equal to matrix B with this notation, this means B minus A is positive semi-definite. Okay. So when your objective function is relatively, so this is relatively alpha strongly convex and beta smooth with respect to pi compared to pi, then we can guarantee roughly the same result as in alpha strongly convex and beta smooth convex function with mirror descent approach. Okay, so this is very interesting and nice result. If you can find very nice mirror map pi so that your objective function is relatively alpha strongly convex and beta smooth and alpha and beta is very close to each other, then we can speed up the convergence. Okay, so for instance, if your original objective function contour looks like this with a simple gradient descent algorithm, the convergence speed was not so fast because the gradient scale this direction and gradient scale this axis totally different. Okay, But if you use some very nice pi mirror map, so that the pi contour also looks like this, almost the same, then essentially we can make a very close alpha and beta, relative alpha strongly convex and relative beta smooth. Okay. So if we can find very nice pi function that satisfies this condition, and we can make alpha and beta close to each other, then basically we can make a very fast convergence. The proof is not difficult. So from the definition of Bregman divergence, we can write fx star is equal to fxt plus gradient of fxt transpose x star minus xt plus Bregman divergence f x star and xt, right? And so here I rewrite, I bring the same term here, and I rewrite fxt using the definition of Bregman divergence, right? And again, from the definition, no. So for this equality, I just bring this one to here. So same term here, and I just add this one and this one to obtain this. Okay, because we share the same gradient fxt transpose this and this, so we can rewrite this term and this term by this. Okay, so for the next equation, here we use the same term, this and this, right? And I just split this term by this plus this, a plus b, right? Okay, and for the next equation, I use this definition, right? So note that for this proof, I do not consider the constraint set. So this theorem valid for non-constraint case. Okay, when there is no constraint, then we have a theorem 4.3. So since there's no constraint, yt plus 1 is equal to xt plus 1. And we know that the gradient of pi xt plus 1 is equal to gradient of pi xt minus gamma times gradient of xt. Right. So using this equation, so I just bring the first 4 terms. I just rewrite first 4 term here, and I just replaced this gradient of fxt transpose using this notation. Then we have this from the definition of Bregman divergence. Okay, and then I used this property, the beta relatively smoothness property. So from this, I can remove this one, I can remove this one, and this one with this inequality sign. Okay, so therefore from the previous proof, we have this inequality. Okay, therefore we have, when we consider the Bregman divergence x star xt plus 1 and the Bregman divergence defined with pi function minus x star xt Bregman divergence, then from the definition of Bregman divergence, we can rewrite this subtraction equal to this. Essentially, this comes from the useful identity, this one. So I just use this one. Okay. And then from the definition of xt plus 1, gradient of pi xt minus gradient of pi xt plus 1 is equal to gamma times gradient of fxt. And this inequality we obtained from the previous page. And for this inequality, I can use the fact that fx star is the minimum point, so x star is the minimum point, so fx star always less than or equal to for any fx t. So this becomes negative, right? And for this inequality, I use the fact that x star and xt Bregman divergence with respect to f always low bounded by alpha times the Bregman divergence with respect to the pi function. Okay, so now we have this inequality, which means every iteration we can reduce the Bregman divergence with this factor 1 minus alpha over beta.